Okay. Just a reminder, there's no class on Monday for our President's Day holiday, and I know the high school, the Rockwood system, is closed also on that day. And then the homework number 4, that's due a week from today. So what we're talking about here is we're talking about functions of more than one variable. So generally we're talking about functions of x and y. And here we're talking in 14.3 about something that they're partial derivatives. So we had started this the last time. There are 2 separate partial derivatives for a function of 2 variables, and we note them as either fx or fy, where we just put a subscript there, or we can use a variation on the Leibniz notation where that symbol is the lowercase delta. Now, when we do the partial derivative with respect to x, the way we do it is we treat y as if it were a constant. So treat y like a constant. And then when we take the partial derivative with respect to y, we treat x like a constant. Okay, and then let's remember what that means then from functions of single variables. So therefore, the derivative of a constant by itself is equal to 0. All right, so we're going to recall that. And then if the constant is multiplying a variable, it stays multiplying the variable. Is multiplying a variable, it remains, or stays, remains multiplying that variable. And we did a couple of examples. I'll do another one here just as a reminder. With the second example we had done last time, the chain rule is alive and well. So we don't want to forget to use the chain rule. Okay, so the one that I want to start with then today is this, fxy equal to the natural log of 3x squared y to the 3rd power plus 4y minus 5x. Okay, so function of 2 variables, and we want to let's first start by getting fx, and so that's the derivative with respect to x. So I'm going to write down as a reminder to myself that I'm going to treat y like a constant when I do this derivative. Now we need to remember a derivative of the natural log. How do we get that? Well, it has a numerator and a denominator. The denominator is just the function itself behind the natural log. So therefore, I'm just going to repeat in the denominator the full expression, 3x squared y to the 3rd plus 4y minus 5x. All right? Now, in the numerator, we put the derivative of that function. Okay? So in the numerator here, I'm going to get the derivative of, so I'm going to treat y like a constant, and I'm going to get that derivative. So let's go term by term through this expression in the parentheses. So for the first one, 3x squared y to the 3rd. That y to the 3rd is as if it were some number to the 3rd power. It remains unscathed. It stays there as it is. And I just then do the derivative of 3x squared, which is 6x. So I get 6x y to the third power. Okay. And then we move on to the next term and the next term. Now, what's going to be the partial derivative of 4y with respect to x? It's going to be 0 because it's strictly a constant. There's no, the variable at this point in time is just the x variable. The y we're treating like a constant. So that's going to be 0. And then the derivative of minus 5x is just going to be minus 5. So that's our fx. Now let's get fy. Now with fy, that's the derivative with respect to y. So I'm going to note on my paper that I treat x like a constant. And again, same deal with the derivative of the natural log. I'm going to put the entire expression in the parentheses in my denominator, first of all. 3x squared y to the third plus 4y minus 5x. And then in the numerator, I'm going to make sure that I remember to treat x like a constant. Okay. And go term by term this time around. So I have 3x squared y to the third. Y is my variable. X is just my constant. So I think I get 9x squared y squared. Okay. X squared just stays there. All right. Then derivative of plus 4y. This time I'll just get plus 4. The y will go to a 1. And then the derivative of negative 5x. X is a constant. There's no variable. We go to 0. So this is my partial derivative then. And notice these two look very much different as far as what is in the numerator. Okay. So they are two entirely separate derivatives. Okay. Okay. Now we're going to get to more of the geometric significance. I indicated the last time that I had something which a little bit better indicated what these are, and we'll be seeing that in just a couple of minutes. Okay. The type of problem I want to do next here involves implicit differentiation. Okay. So this involves implicit differentiation. Okay. So maybe we can just look at a problem in a single variable before we do this here. So this is from single variable calculus. This would be, you would have been introduced to this in Calc 1. Say we have x squared y squared plus 3xy minus 2y to the third plus 5 equal to 0. Okay. So where y is a function of the variable x. All right. And so we want to find dy dx. All right. So this involves implicit differentiation. So let's see what we might get here with this. Okay. Now, let's see. We're taking the derivative of everything with respect to x. Okay. So what about this first term here? We have x squared y squared, and I'm doing this derivative with respect to x. So I think I need to use the product rule with this. So let's start with x squared then do the derivative of y squared. Well, we're going to take the 2 down, reduce the exponent by 1, 2y, but then we have to continue with the chain rule because we're doing the derivative with respect to x, and that would be then times dy dx. Now we have to do the other half of the product rule. So now I do the derivative of x squared, which is 2x, and then I multiply that by my other function, which is y squared. All right. Okay. So that's our first one. Now any question on the first one? Product rule, and we're going to need the product rule on the second one also. So here's our second one then, and again, so plus 3x, and then y goes to a 1, but we take the derivative, then we do the derivative, so that would be dy dx then, and then plus, then we do the derivative of the 3, which is 3x, which is 3, and we're multiplying that by the y. Okay? So again, product rule. Okay, the next one's a little bit simpler. We just have a minus 2y to the third. We do the derivative. So we're going to take minus 2 times 3 minus 6y squared, but we have to complete it with the chain rule, times dy dx. Then we have our 5. Well, the derivative of 5 is 0, and the derivative of 0 is 0. So we have this equation. And then remember what we had to do then. We had to collect all the terms that had dy dx in it. And so we had dy dx, and so let's collect them. We have 1, 2, 3 terms with dy dx. So that would be, the first one is 2x squared y. The second one is plus 3x. And the third one is minus 6y squared, close parentheses. And then let's put on the other side of our equation then the other terms. We have this term and this term. So I'll flip them to the other side. That'll be minus 2xy squared minus 3y, all right? And then finally, to get the dy dx, I just divide by this entire expression. dy dx equals, okay, minus 2xy squared minus 3y, all over the expression, multiplying, so that 2x squared y plus 3x minus 6y squared. So the important thing with that implicit differentiation is this whole deal of remembering to use that chain rule, and of course to remember that all the derivative rules still apply, like the product rule. Okay. Now we're going to do the same kind of thing with functions of 2 variables, and we're going to get the do the implicit derivative. All right. So here's our example with this. Suppose that we have the variable z, and suppose z is a function of x and y. All right. And if it is defined implicitly by the following: x to the third plus y to the third plus z to the third plus 6xyz equals the number 1. Okay. All right. So in other words, it's defined, z is defined implicitly because we don't just have z on one side of the equation. Now, what we're asked to find is find dz dx and dz dy. All right. So let's first of all do dz dx. Now, for dz dx, I'm treating y as a constant. So I'm going to make a note of that. And I have to do the implicit differentiation. Implicit differentiation. All right. So again, let's go term by term with this. All right, dz dx. So our first term is x to the third, so that's easy. That's just got x in it. That's going to become 3x squared. The second term, okay, we do the derivative to get 3y squared, but we have to complete with the chain rule times, hold it. Yeah, right, constant, yep, thank you. So we're actually, didn't even need to write that down. Y is a constant, that's just going to go to 0. So we just ignore that. Now, z then, so let's plus, and then we do the derivative of z to the third, so we have 3z squared, and then we complete with the chain rule of dz dx. And notice I'm using the delta, the partial derivative symbol with the delta, the lowercase delta. And then let's go then to the last term here. We have 6xyz. Now, here, y is a constant as far as we're concerned, but x is a variable. So we're going to have to use the product rule here. All right? Another way that we can look at this is 6 times y times xz in this case. All right. So the 6 is a constant. Y is treated as a constant. So I can really just kind of keep them there to the right, and then go on and do my product rule with the x and the z. So I have the x, and I do the derivative of the z, so it's dz dx. And then I take the derivative of x, which is 1, and I multiply it by the z, and I get plus z. All of this is being multiplied by my constant 6 times y. Okay? And then this all equals the derivative of 1 is 0. Before I go any further, is there a question on this one here? And it helped to kind of rewrite it a little bit so I have the constant stuff over there to the left. And then I have to do the product rule with the x and the z. All right, so let's then collect all the terms with, let's do a little algebra here. So 3x squared plus 3z squared dz dx. Let's distribute here. So we have 6xy times dz dx plus 6yz. And that all equals 0. And now let's just have the terms that are multiplying the dz dx. And so that's the 3z squared and the 6xy. And then let's put the other 2 terms over to the other side. Minus 3x squared minus 6yz. And then finally, let's divide to isolate the dz dx. So we get minus 3x squared minus 6yz all over 3z squared plus 6xy. All right. And by the way, this could be simplified a little bit. Notice all the terms have 3's in them, so I could always knock out a 3 and reduce it to what? Minus x squared minus 2yz over z squared plus 2xy. Okay. All right, now let's just do a similar thing then for the other dz dy. Okay, dz, dy, and I'm going to note here with dz, dy, I'm going to treat x this time as a constant. Okay. All right. So go term by term here with this. So now it's with respect to y. X is a constant. So this time that first x to the third is all a constant, no variable. That goes to 0. I don't even need to, of course, write the 0 there. Then I do my implicit differentiation with the y to the third. So that's going to be 3y squared. That's just going to be 3y squared. Okay. Because it's with respect to y, so I don't have to do anything more with that. Then let's do my z to the third. Okay, I'm going to have to use the chain rule, 3z squared, and then times dz dy. Because z is a function of both x and y. And then finally, then I have this last thing. Now this time, x is a constant. So actually, it's set up very nicely already. I've got the 6x in front, 6x times y times z. So just like with the other one, I'm going to keep the constant stuff initially just right out there as it is, and then I'm going to do that product rule again. Okay, so we have y times z. So we're going to have, okay, y times the derivative of z with respect to y, and then plus the derivative of y with respect to y is 1 times the z. And that all equals the derivative of a constant, which is 0. All right, again, we're going to do the same algebra stuff. 3y squared plus 3z squared dz dy. Distribute, I have 6xy dz dy plus 6xz, all equals 0. And then combine terms. So dz dy, what do we have with that? 3z squared plus 6xy. And let's put the other stuff over there. We have a 3y squared minus 3y squared minus 6xz. And then divide, and we're done. So we find dz dy is equal to minus 3y squared minus 6xz all over this 3z squared plus 6xy. And again, every term has a factor of 3 in it that I can reduce to minus y squared minus 2xz all over z squared plus 2xy. Okay. So on homework, and I can guarantee you elsewhere, you will have an implicit differentiation problem. So again, don't forget to use the chain rule and product rule when you need to, and go from there. All right. Now, I'm going to get back to kind of the geometric significance of these partial derivatives. Okay. So let me put this down here first. Okay. Okay, we had, see if I still have another one of these. Yeah, let me use this. Here's our surface. Here's our x, y, and z axes. This kind of darker gray is our surface. And this is the point on the surface, capital P, that we're interested in. All right. Now, if we cut, and we showed this the last time, if I cut this surface with a vertical plane along the y direction, I will get a curve. It'll cut a curve into my surface. If I cut it with a vertical plane in the x direction, it will cut a curve, another curve in my surface. on each one of these curves that are on my surface, I can draw a tangent line that just touches that curve right there along the surface. So I have a tangent line here that goes in the y direction, a tangent line that goes in the x direction. Okay, so let me put this down then. At every point, now a point on our surface is going to have the x-coordinate, the y-coordinate, and remember the z-coordinate is the function value. So that's another way of representing a point on the surface. X value, y value, and then the fxy value, the z value. At every point on our surface, there is a tangent line going in the x direction. There is a tangent line going in the x direction and a tangent line going in the y direction and a tangent line going in the y direction. Now, we remember from single variable calculus, y, x, we have a function, f of x, and we draw a tangent line. Let's say this is at x sub naught. The slope of that tangent line is the derivative value at x sub naught. So m is equal to f prime evaluated at x sub naught. So it's the same thing here. We've got these two, now we have two tangent lines. And the slope of the one is the value of the partial derivative with respect to x. The value of the other is the partial derivative value with respect to y. Okay? So the slopes of these two tangent lines are given by the number values of fx and fy respectively. Remember, slopes are numbers, they're not mathematical formulas. So the slopes here are going to be some number that we get when we plug in the x and y's into our partial derivatives. Okay? So let me show you this, this nice thing. All right. This should be it here. All right. Geometric interpretation of partial derivatives. Now, this has got three different diagrams on it. So this first one, first of all, this is our surface, this meshed area where the lines in the one direction are going along the x values, in the other direction they're going along the y values. Now, this big blue dot is the point on the surface that we're looking at. Now, notice here that we've got a couple things emanating from this blue dot. We have a blue line, if you can see that, and we also have a green line. Maybe you can see it a little bit better here. Green line, blue line. I believe here the blue line is going in the x direction, and the green line is going in the y direction. So at every point, we basically are cutting these two curves. These are our two curves that we get by slicing the surface either with a vertical plane either in the y direction or in the x direction. And what we get is this curve. So the curve varies depending on where we are on the surface. Now notice that what we have then connected with each of these two curves are red lines. And these red lines are the tangent lines. So this red line here is the tangent line for this green curve, which is along the y direction. This other tangent line here is the tangent line for the blue curve that goes in the x direction. So at every point we have two of these tangent lines. And notice how it all just very much goes all in different directions for these tangent lines as we move this thing through our surface. Okay? Now let's go to the next thing then, down here. Okay, this next diagram again shows let's move this thing. Again shows the blue line and the green line, the two cross sections as the surface is being cut by those vertical planes, all right? But what this graph now shows us is the following. Notice that these arrows now that are emanating, these red arrows, are changing size. Now notice right here, this one red arrow in the green direction suddenly has gotten very large. But if you look here, this is where the surface is increasing quite a bit, and this is in the y direction along this green line. The size, the magnitude of this red arrow, they programmed it to be the size or magnitude of the partial derivative value. So here we have a big partial derivative. Our x is not so much. Now, I think if we go, somewhere we're going to have a bigger x value here. What do we have here? Yeah, here we had, now here, it turns out that along our blue, we have a bigger increase, so therefore the value of our partial derivative with respect to x is a bigger value, okay? Because we're going to have a bigger, remember, derivative is going to give us that slope. So we're going to have a bigger slope, we're going to have a bigger partial derivative. And then when we get to the flat area over here, they both end up looking pretty much the same in value, okay? And what is this last one here? Now, this last one is basically the same as the second one that we just looked at, except what they add in here now is something we'll be talking about in the next section, actually, is the tangent plane. So notice again, we still have the blue dot here. We have our blue and green curves, and we have our red arrows that represent the size of the partial derivatives. But now we have this kind of flat rectangle that is also following, enclosing our dot here. And the two partial derivatives are actually, this is a plane, and it's called the tangent plane. And this tangent plane, both of these vectors from the fx and the fy can be considered as lying in this tangent plane as it moves around. So as our vectors move around, our tangent plane is going to be then also moving around. And it's a plane, so it's strictly a flat, two-dimensional surface, and it just follows right along our partial derivatives. So I think it's just a good illustration, certainly better than anything anybody could do on a board. Okay. So let me get that down. Right. Okay. Here, let's look at a problem here connected with these slopes. So let's look at an example. Let's say our function is fxy is equal to 4 minus x squared minus 2y squared. All right. And basically, let's suppose we're, shall we say, quote unquote, interested in the point where x is equal to 1 and y is also equal to 1. All right? And what we want to find is then find the slopes of the two tangent lines at that point. Okay. So to do that, we have to get the fx and we have to get the fy. So let's look at the fx, and here we're going to treat y like a constant. So I'm going to write that down. And so fx is going to be what? What would fx be for this function? Yeah, negative 2x. This is a constant, of course, and then this is all just a constant because we're treating y like a constant. Both go to 0. We do the derivative here. It's minus 2x. So therefore, when we're looking at x equal 1, y equal 1, then we're looking at, let's do it this way. fx at 1, 1 is going to be minus 2 times 1 is going to be negative 2. And so this is the slope of the tangent line in the x direction. And then similarly, let's get fy, and now we're going to treat x like a constant. Okay, so we're going to get minus 4y, right? The first two terms become 0. And now, so we find the value when x and y equals 1. So that's going to be minus 4 times 1, negative 4. And so that's the slope of the tangent line in the y direction. Okay. All right. So that's pretty straightforward. You just get the fx, fy, plug in to get your number value, to get your slope of the tangent line. All right. So guess what? We're talking about first partial derivatives. So guess what? We, of course, have second partial derivatives. Right. So we're now going to look at higher derivatives. And just like with functions of a single variable, when we do a derivative of a derivative, we just follow the same derivative rules. We're just starting with a derivative, okay? And so that's what we have here. So I want to really first look at the second partial derivative. Now, we actually have 4 of these. Okay, we can start with our fx, do its derivative with respect to x, so I'm putting it in parentheses, its derivative with respect to x, and we write that in shorthand as fxx. Another way of writing this then is to take our df dx, I'm using now that Leibniz notation, do its derivative with respect to x, and then we get delta square f over delta x squared, like that. And that's similar to what you had, of course, in Calc 1. Now, we can also then start with fx and do its derivative with respect to y and have, and this is called fxy, right? So these subscripts are in the order in which we're doing the derivatives, okay? In the order we do the derivatives. And of course, we can write this with the other. So we're starting with delta f delta x, but then we're doing its derivative with respect to y. So we have that. And this then in shorthand is delta squared f over delta, let's see, which one comes first? Delta y, delta x, like that. Delta y, then delta x. All right. And then we can do the same thing with starting with fy, because remember we have two first partial derivatives. And we can take its derivative with respect to x, and that gives us fyx, like that. Of course, if we want to, and believe me, I'm certainly not going to be using too much this other notation. It's a pain, actually. Df dy, and then we're doing its derivative with respect to x. So that gives us delta square f over d delta x delta y. And then we have a fourth one where we again start with fy, take its derivative now with respect to y. This is fyy, or we can write it delta f delta y, do the derivative with respect to y, and that's equal to delta square f over delta y squared. So you see we have four of these. Now there's some good news though about these, is that if, and let me write it down here, good news, always good to pass on some good news. All right. Clairaut's theorem. All right. If fxy and fyx, if those two second partial derivatives are continuous, and guess what, folks, for the functions we're looking at, they're certainly going to be continuous, then we have this nice piece of information. Then fxy is the same as fyx. So therefore, if those are continuous partial derivatives, second partial derivatives, if I first get the derivative with respect to x and then get it with respect to y, I'm going to get the same thing as if I got the derivative first with respect to y and then got it with respect to x. So what we're saying here, up here, these two up here will be the same, fxy and fyx, okay? All right. Now what we're going to do next then is, and then we'll take a break, is to get some second partial derivatives, right? So example here, if we have fxy equal to this, so this is actually a nice one because it's a nice polynomial function. So that certainly makes life a little easier. fxy is x to the third plus x squared, y to the third minus 2y squared. And we're asked to find all the second partial derivatives. All right. Okay, so obviously, what do we have to find? To find the second partial derivative, what do we have to find first? Right, we have to get the first partial derivative because otherwise we'll never get to the second. Acacia's looking. What's that now? How many points? Well, how would I know the answer to that? Okay. Actually, this problem, well, okay, let's work it and let's see how many points we think it might be worth. All right. So let's get the first partials first. So let's get fx first. We're going to treat y like a constant. Actually, as far as getting second partial derivatives, I can't think of an easier type of function to use than something like a polynomial like this. All right? What might not be so pleasant to use would be something where we have to use the chain rule and then the product rule. All right? So we'll see what happens here. All right, so we're going to treat y like a constant. So therefore, let's go term by term. X to the third, the derivative is going to be 3x squared. Okay, second term, y is a constant, so y to the third is going to stick around, and we get the derivative of the x squared. So that's 2x times y to the third. And then the third one, well, that just drops off the map because it's strictly a constant. Now let's get fy, where we treat x like a constant. Okay, this time around, the first term drops off the map. And then the second term, what are we going to get for the second term? Mm-hmm. 3x squared y squared. Just keep that x squared just as it is. Don't mess with it. Do that derivative of y to the cubed. We get 3x squared y squared. And then finally, our last term is just going to become minus 4y. Okay. It's minus 2. Here, it's minus 2y squared. Yeah. Okay. Okay. So that's that. Now let's get say fxx then. All right. So with fxx, this is what I start with. I start with that fx, and what am I going to treat at which of the two variables am I going to treat as a constant? I'm going to treat y as a constant. Okay, so you see me writing this down, and you might want to do that at first so that you don't get sidetracked. Okay, so this is what we're starting with. We treat y like a constant, so term by term, 3x squared becomes 6x. And what does that second term become? 2y cubed. The x is going to go to a 1, so the 2 and the y cubed stick around as they are. While we're at it then, let's get fxy. Now again, we're going to be starting with the fx. But this time, what am I going to treat as a constant? Right, I'm going to treat x like a constant. All right, so I'm starting with this, 3x squared plus 2xy to the third. Okay, the first term goes to 0, 3x squared, all a constant. Second term, 2 is a constant, x is considered a constant, so I do the derivative of y to the third. So I get, what do I get? 6, bring down the 3s, 3 times 2 is 6xy squared, and that's my fxy. And guess what? That's also my fyx. So I killed 2 birds with 1 stone with that one because they're equal to each other here. So the only other thing, I need to get 4 of these, the only other one I need to obtain is fyy, right? I've gotten 3 of the 4. So with fyy, I'm going to now be starting with my fy. I'm going to do the derivative with respect to y, so I treat x like a constant. All right. So, first term is going to become what? Six x squared y, yep. Bring down the 2, 2 times 3 is 6x squared stays the same, y. All right? And then minus 4y, derivative with respect to y, that's a minus 4. Okay? And so I have all 4 of them, and life is good. And that's I don't think that is something that necessarily would have to be a tremendous amount of points. That one's not too bad. Can I get a grudging not too bad from? Yeah, okay. All right. Could be a lot worse. All right. Last, just, might as well just one last, well, actually it's not one last thing. So why don't we take a 5-minute break now and then we'll finish up this section. Oh. Hello.
Sorry to be late. Still got the sheet by my house, so it's hard to. Yeah, I know, it's not someone's here.
It's just like those localized.
Right. It's really hard to control though.
Is it really?
Yeah.
Okay.
I do it 4 times right. Great comment. I'm not doing something else.
I'm glad you got here safe. That's important.
I copied the textbook real quick.
Oh. The project.
Well, I'm missing my best friend on a Valentine card.
You're going to have who do?
I'm gonna make my best friend a Valentine.
Oh, that's nice. Very nice. That's a big. That's a big.
My friends can do that.
Okay. All right. That's nice.
Yeah, I was trying to do it to Truman, and I got a power that that got really complicated because obviously I'm not at Truman today to give her power.
Right.
Like arrange to get them to her to a friend and talk to her. And I had to give flowers to that friend of a friend to thank her for help. So.
Oh my, that can go on to infinity. Goodness. Yeah.
Well, I was up at Kirksville last week, so I managed to give that present to save myself the introduction.
There you go. I imagine they're having some good weather right now.
Apparently, the fun thing on their campus is the stuff they put on the snow, it's the snow melt, right? Apparently they have school themed snow melt where it's in the school colors, so all their driveways just in such a
Why not? Make a lemon a lemonade. Do something with it.
Right.
That's my motto. Yes, sir.
Where the tangent is coming from here?
Oh, sure. Basically, all right. Okay, so you did this, which is fine. All right, so you get, basically you get 4 d theta, right? So that's 4 theta. But here, okay, if this is your t, then, so here you're going to have theta, right? Theta is going to be tan inverse of t.
I get it. It is my variable.
And you really could have saved yourself some trouble if you just try to remember that over 1 plus t squared is tan inverse.
Okay.
You know, that's just one of those things that, you know, there are a lot of formulas to remember, but if you can remember that one and the fact that the square root of 1 over 1 minus x squared is the sine inverse of x, that's another one to kind of just always keep around. Okay. And if there's anything else we can talk about. Anything else, Charles? All right. All right. So we did the partial derivative, second partial derivative. So, of course, needless to say, we don't necessarily have to stop at the second partial derivative. We can just keep going on a long time. But I'm just going to look at one example of a partial derivative of order 3. All right, so here we're given fxy equal a cosine of 7x plus 2y. So we can see we're going to be using chain rule here with this. Oops, let me get this over here, like that. Okay, and what we're asked to find is find f of x, x, y. All right, okay. So we just do them in order here. Let's first get fx. And so we're going to treat, you know, again, we're going to treat y like constant. And of course, we're going to use the chain rule. So the derivative of the cosine is the negative sine. Actually, we keep the whole expression there in that parenthesis, 7x plus 2y. And then we're going to do that partial of 7x plus 2y with respect to x, and that is going to just give us a 7, because the y is a constant. So therefore we get minus 7 sine of 7x plus 2y, and then we repeat the process. Now we get fxx. So again, we're going to treat y like a constant. And so now we have the derivative of the minus sign is the minus cosine. So this is minus 7 cosine of what's inside. And then again, with the chain rule, with respect to x, we're going to just have a 7. The 2y will go to 0. So this gives us minus 49 cosine of 7x plus 2y. And then to finally get the fxxy, now we're going to treat what as a constant? We're going to treat the x like a constant. So let's see, we've got the derivative of a minus cosine. That'll give us a sine, so we have 49 sine. Again, keep the inside. Notice the inside doesn't change all along this whole chain rule. And now we're treating x like a constant, so we're going to multiply by a 2 here, right? The 7x will go to 0. So the final answer here is 49 times 2 is 98 sine of 7x plus 2y. And we would have gotten the same result if we had done fyxx or fxyx, any of those, as long as it had 2 x's in it and a y, since these are all continuous, it would have given us the same result, all right? Okay. All right. Then the last thing on this, in this section, just introduces something what's called a partial differential equation, and it shows that basically we can use these partial derivatives to verify that something is a solution. So let me, partial differential equations. Now, the key word there is partial. In Calc 2, we were introduced to differential equations. So just remember this, differential equations, just as an example, say something like dy dx equals 3x squared over 2y, something like that, and we ended up solving for y of x, solving for y. Does anybody remember how we did that, say, in this, with this particular kind of thing, what our first step would be? Yeah, separate the variables, right. Basically cross-multiply and separate variables. All right, but anyway, I just wanted to show that's the kind of thing we saw in Calc 2. Now here we're talking about partial differential equations. So a very famous one is Laplace's equation. And it has partial derivatives in it. And it models, the thing with these partial differential equations is that their usefulness is that they model certain physical phenomena. So this thing models heat conduction and fluid flow. So here's the equation, delta squared u over delta x squared plus delta squared u over delta y squared equal to 0. And this is where our function u is a function of both x and y. So u is a function of x and y. Here we're doing the second partial derivative. So this is really u x x plus u y y, and it ends up equaling 0 for and if we're in the model. So the type of problem that you might see that's connected with this is the following. You might be given a function and ask that it does indeed satisfy this particular differential equation. So the way we do that is we get the second partial derivatives and see if they add up to 0. All right? So here's the type of thing. Example. Show that u of xy equaling this, e to the minus x times cosine of y minus e to the minus y times cosine of x is a solution to Laplace's equation. What we do here is we plug in the partial derivatives, get the partial derivatives and plug them in. We get uxx and uyy and see if they add up, uxx plus uyy adds up to 0. That's how you do this. All right, so that means we've got to get these partials then. So let's start with, say, ux. And ux, that means we're going to treat y like a constant. All right, so okay, here it is right up here. All right, So y is being treated like a constant, so what do we get for that first term for ux? What's the derivative of e to the minus x? Yeah. With the chain rule, negative e to the negative x, and we just keep that cosine of y as a tag along right behind it. And then on the second term, again, y is a constant, so I need to get the derivative of the cosine of x, which is the negative sign. So that's the negative sign, but notice I have a minus here in front, so the derivative of the minus cosine is the positive sign, so I get a plus here. I keep the e to the minus y because that's just considered a number, and then I have sine of x. All right. And now I have to get the derivative again, uxx. Again, y is a constant. So what do I get now for the first, what does the first term then become? Yeah, the minuses then end up, with the chain rule, end up canceling themselves out again. So I get e to the minus x, again just plain cosine y, and then plus, okay, y is a constant, derivative of sine is the cosine. So e to the minus y times the cosine of x, and so that's my uxx. All right, so let me put a box around that. Now let's get the uyy. So let's get uy first of all. So that means x is a constant. So here's where we're starting. X is a constant, e to the minus x cosine of y. So that's derivative of that. It's going to be what? Minus, because the derivative of the cosine is the minus sine, so minus e to the minus x sine of y. And then what will I get for the second term then? The derivative of minus e to the minus y times the cosine of x. X is a constant. Plus e to the minus y cosine of x. Right. Where again, chain rule, the double minuses will cancel each other out. Is everybody following just basic chain rule stuff? You just have to be careful of treating that other variable like a constant. Now we're ready to get u, y, y, and again, x is going to be a constant. So let's see, what does this first one become then? Okay, derivative of sine will give us the cosine. So it's minus e to the minus x cosine of y. And then the second one then becomes what? Yeah. Minus e to the minus y, again chain rule, times the cosine of x. So this is the second one. And so if we ask ourselves, is uxx plus uyy, does that end up equaling 0? And let's see, I think it does. We have e to the minus x cosine y. Here we have minus e to the minus x cosine y. Those add up to 0. And here we have e to the minus y cosine minus e to the y cosine. That adds up to 0. So yes, it satisfies the equation. Okay. So you might see one of those types of problems in the future. Yes, Jenna? It tells us that if we're looking at certain physical conditions, that this is actually what happens, is that and you're asking me about physics here, all right? So that's not my strong point. I have had a course in partial differential equations, but basically, I don't know. If we are modeling, say, heat conduction, that's all I can tell you, then it's going to be whatever we're talking about is going to satisfy this equation here.
So every single time that we get UXX and UYY, they should equal 0.
If we're talking about something satisfying this equation. No, okay, I don't want you to think that every time a UXX and a UYY, no matter what the function is, that they add up to 0. All right? With this particular function that we started with, this one right up here, yes, they did add up to 0, but not in general. Okay? But with this one, yeah, it did, which means that this satisfies our Laplace differential equation right here. But there's only going to be some functions that do this, all right? Not in general, so please don't go away by thinking that UXX, no matter what the function is, UXX plus UYY is going to equal 0, all right? Only with some functions. You'll be given the function, you'll be asked to verify that it's a solution, just like we did here. Okay. All right. That ends this section then. So I want to get a sum of a start here since we don't have class on Monday. Yes. On the next section, 14.4. Now, the homework that's due on Friday is these first 3 sections, 1, 2, and 3, all right? So 14.4, we're talking about 2 topics. We're talking about those tangent planes that I had showed you an example of in that one nice program, tangent planes, and the second topic is linear approximations. Okay. All right. Again, we're starting with this basic same type of diagram that I showed you before. Again, the darker gray is the surface. This is a particular point. We drop these vertical planes through them along the x direction and along the y direction, and those cut 2 different curves in our surface. One curve goes in the x direction, the other in the y direction. And then each of these curves gives us a tangent line. So we have one tangent line here, and we have a second tangent line here, all right? And what those 2 tangent lines give us is a tangent plane. All right. So let me put some stuff down in English. It's kind of a rehash of what you have here before. Let's look at a point. I'm going to call it capital P, and I'm going to say that its coordinates are x sub 0, y sub 0, and z sub 0. So it's in 3 dimensions. And this point is on a surface S given by z equaling a function of x and y. All right, so we know that, again, we have x and y, and we have z. For every point in the xy plane, we get a corresponding z point. This collection of these points gives us our surface that's floating around in midair, so to speak. All right, and this is the surface. Z is equal to fxy. All right, so we got a point. This is, say, a point P, and at that point, let's cut the surface with 2 vertical planes. at that point P, cut the surface with two vertical planes, and those planes would be x equaling x sub naught, y equaling y sub naught, okay? Where the y value is constant, and the x value is constant in the other one. And as I had shown, this gives us two curves. We can call it C sub 1 and C sub 2. That's on the surface. And each of these curves has a tangent line. Each curve has remember, tangent lines are straight lines, has a straight tangent line. And I'll call them T1 and T2, respectively. Now, these two lines, they cross each other right at that point P. These two lines, T1 and T2, they cross at the point P, and they give us, and they lie on the same plane. Remember, given two straight lines, that determines a plane. Recall, given two straight lines, that determines a plane. Just like 2 points determine a line. 2 lines determine a plane. Okay? Now, so here's our definition of now this is all leading up to this tangent plane, because that plane is the tangent plane. The plane, so this is a definition, the plane containing point P and containing the two tangent lines, L1, I'm sorry, now I'm just naming them something else, T1 and T2, if this plane is called the tangent plane, to the surface F at point P. All right. Okay. So we've got this surface floating around. We've got a point on there. We can cut it so that we have a curve going this way and a curve going this way. This curve will give us one tangent line. This curve will give us another tangent line. And both of these lines then form a plane that are in a plane called the tangent plane. Okay. The first thing I want to give you then here is the equation of the tangent plane. So you will need to remember this. So I'll put an asterisk by this. The equation of this tangent plane is, z minus z naught equals partial derivative of f with respect to x We're evaluating that. We're going to get a number. We evaluate it at the x naught, y naught. Remember, our point P is x naught, y naught, and z naught. And then that partial derivative is multiplied by x minus x naught. Then we have to do the partial derivative with respect to y. Fy, again evaluated at x naught, y naught, but this time this is multiplied by y minus y naught. This is actually very similar to, in two dimensions, single variable, the point slope formula. Let's just look at that for a second. Basic algebra, 2 dimensions. Or actually this is, well, it's really, let's just say one variable. Let's put it that way. One variable. The point slope formula of a straight line, of a line. Remember, it's y minus y naught equals m times x minus x naught. And remember, m is actually the value of the first derivative. So this is dy dx evaluated, put a line there, evaluated at that x naught. So this is just an extension into 2 dimensions of that formula. All right. So let's look at an example of something you might be given with this. Example. Find the equation of the tangent plane to, and here's our surface, z is equal to x times the sine of x plus y. So this is our f of xy, fxy function, and we want to find this equation at the point where x is equal to -1, y is equal to 1, and therefore z has to be equal to 0. I want to make sure we understand why z has to be equal to 0 here. This is our surface. For every x and y, we have a corresponding z value. If x is equal to -1, and then we do the sine of x plus y, and y is equal to +1, we are therefore doing the sine of 0. -1 times the sine of 0. So the only value that z can have here, of course, is 0. So this is what we're asked to do. Now, to do this, we have to get the number value of the partial derivatives at this point. So let's get the values of fx and fy at this point, -1, 1, and 0. Okay, so obviously to do that, we have to get the formula for fx and fy. So let's obtain fx first. Here we're going to treat y as constant. And this is our function here, fxy, x times the sine of x plus y. Okay. So why don't we just take a second to figure out what that might be. Do-do-do. The theme from Jeopardy. Okay. All right, well, let's see what maybe we got here. Anybody want to hazard to say what they got for fx?
Minus x plus y, x
Okay, sine of x plus y, and, I'm sorry, Mary, what else?
plus x plus
Okay, and it looks like you used the product rule to do this. So the product rule is needed. So what do we have? This first one is the derivative of x times the second function, sine of x plus y, plus, and then the first function, x, times the derivative of the sine is the cosine. And then, of course, since it's just x plus y in there, the further use of the chain rule just gives us a 1. So that's fx. So now we need to plug in fx when x is equal to -1 and y is equal to 1. So let's see, what do we get for that value? Sine of what? -1 plus 1 there, plus -1 times the cosine of -1 plus 1. And that's all going to simplify to -1, right? The first one is 0, this is 1, so it's -1. Okay, so we've got that part of it. Now we have to do a similar thing then with fy. And so with that, x is constant. All right, so let's see, where's our function? Here's our function right here. X is constant. This one's a bit easier actually, because why is this one a little bit easier? I don't have to use the product rule with this one. If x is being treated as a constant, basically this is just like having a constant times the sign. So I don't have to use the product rule. So no product rule needed. So what do we get? We get x, derivative of the sine is the cosine of x plus y, and then, of course, the derivative of the inside with respect to y is just a 1. So we get that, and so let's again plug in x equal -1, y is equal to 1, and so we have -1 times cosine of -1 plus 1, and that's going to give us the -1 again. All right. So our formula here then, remember here is recall, it's z minus z naught equals that fx at x naught y naught times x minus x naught plus fy at x naught y naught times y minus y naught. So now we just need to fill in everything. Z naught here is equal to 0. So we have z minus 0 equals, now our fx is -1, and now it's multiplying by x minus x naught, but x naught is a -1, so it's going to be a +1. Then our fy, we got a value of -1, and then y minus y naught, well, y naught is equal to 1, so that's y minus 1. So let's make this look a little better. So we get z is equal to what? Minus x minus 1 minus y double negative plus 1. So z is equal to minus x minus y. And this then is the equation of our tangent plane. Right? So being able just to apply that formula, plugging in those values is something that you need to do. Any question on that process? let's see here. I'm thinking this is actually a good place to stop. Don't keel over. Okay, I'm glad you're all seated, because otherwise I'll just get into something and I'll just have to repeat it all again because it's going to seem like forever because it's going to be Wednesday. So anyway, we'll just stop right there and have a great President's Day holiday, everybody. And see you all on Wednesday then.
What was causing your shadow on your
Is it still there?
No, that's
Muha, the tech guy here, let's see, stop recording.